was asking us to find f prime, was asking us to find dy, and was asking us to find f of x, the antiderivative. So first I will differentiate the function, but you know me, I prefer this notation. It's up to you. You develop your own style, I'm sure, at some point in time. So f prime of x will be negative 1 plus x squared to negative 2 times the inner function prime, which reduces to this. So I have f prime, which is negative 2x over 1 plus x squared, of course. Now I have dy, because dy is the same thing, 1 plus x squared times dx. And for uppercase f of x, which is the antiderivative, which function prime is this? Arctangent x plus a constant c. So these were the three answers that the discussion was asking us to find. The derivative, the differential with the correct notation, and the antiderivative, the most general antiderivative, which is this. Okay, moving on. Any questions? Any questions? Okay, so remember what we did so far. Allow me to just go back for a minute. We know what the area represents under a graph. We know how to determine it only for three types of functions. One big type, which is polynomial, but specifically degree 1, 2, and 3. So we know this so far. From I equals 1 through n. Okay, so remember I said that this is the Greek letter S, the summation notation, or sigma, and it's used because it has this shape, and I can write the index at the bottom and the lower limit, and then the upper limit at the top, so it's convenient. But this is also the same thing with, and this is the title of this chapter, the summation with not a Greek letter, but the Latin S, right? But if we stretch it, it will look like this. And you can say, why are you stretching it? I'm stretching it because I really want to have a lower limit and upper limit. So of course the interval in this case is a comma b. So the interval from a to b, and this is called the definite integral from a to b. Of what? Of the same thing. We are not writing it as delta x f of x, but it's the same thing where we have to write it as f of x dx. Okay, so this is the same thing. Either the limit of the Riemann sum, the exact area, exact, no approximation, no squiggling symbol, equals, or the definite integral from a to b from f of x dx. It's still in the same interval, and it's still the product of base times height. Base times height plus base times height plus base times height for all those rectangles. Same thing. However, this is very cumbersome. And you can say, are you kidding me? Look at this one. Yes, I write with a marker. Yes, I write very big. But look at this. Right? Well, for the functions that we looked at, we're going to be able to determine this in one line. So you can say, but then why this? Why are you showing us the limit of the Riemann sum? It's because we need to understand where it's coming from and how it was developed and how we got to this. Exactly like we did with derivatives. If you remember, yes, I know it's been a long time, but when we determined the first derivatives, we used this, the limit as h approaching 0 from the difference quotient, f of x plus h minus f of x divided by h. We understood this, that the derivative is the two concepts put together, the limit and the difference quotient, and then we moved on to rules. differentiation rules, or how to differentiate using power rule, product rule, and so on and so forth. The same thing here. We know now how to determine this area, and now we can move on to what it's called the rules, if you want. So this was cumbersome, like this was, but now this will be similar to the rules of differentiation. Not what I'm saying is the next step up. Okay? Now the question is, how do I evaluate this? I know how to evaluate this, and I'm restricted to 3 functions. But how do I evaluate this? Okay. So here's how we evaluate a definite integral. It's called FTC, Fundamental Theorem of Calculus, Part 2. There is a Part 1. We're going to get to it. But right now, for this, we only need Part 2. Fundamental theorem of calculus requires the function to be continuous. Continuous f of x on a comma b. If the function is not continuous on the interval a comma b, fundamental theorem of calculus is not applicable. Assuming the function is continuous, how do I determine it? How do I evaluate that integral? Here's how we do it. The integral from a to b from f of x dx is the most general antiderivative of this function, evaluated from a to b. But how? Plug in b minus subtract when I plug in a. This is fundamental theorem of calculus part 2 that shows us how to evaluate a definite integral. For definite, what do we mean by definite? It's fixed between a and b. Fixed. Definite integrals. And now we're going to look at those problems that we calculated today, and we're just going to check our work with a definite integral. So you can
Could
say,
you go over what a definite integral is specifically compared to like a non-definite?
It's the area under the graph.
Okay, sounds good.
And the indefinite we haven't discussed yet, and I'll explain what that means. So again, let's discuss this for a moment one more time. Assuming the function is continuous, of course it is. We picked continuous functions. So initially we had this function. Then you made one up for us, which was this. Of course, these are continuous functions. They're polynomial functions. They are continuous on anything you give me. So that is fulfilled in our examples. We're going to work on both of them in a minute. Now the question is, and you should ask, where is your c? You're just saying that this is the most general antiderivative of this, but I don't see the c. Well, when you plug in b and then you subtract when you plug in a, the c cancels out. That's why c is gone. Okay? So now let's go back and look at, I'm on page 9. So we had 2 functions. You gave me this one, 3x squared plus 4x plus 2. And the interval was 0, 4. And then you also gave me 2x cubed plus 5x plus 1. And the interval 1 to 2. Perfect. I don't remember the answers. We'll go back and check. So, in order to find the area, so this is again the summation. It's this s, but it's stretched, but it still means the same thing. It's a sum from 0 to 4 from this function. Of course, dx. There is no integral without dx. Equals. Can anyone help us identify the most general antiderivative, and then we will plug in from 0 to 4. Which function prime is 3x squared?
X cubed.
Yes, perfect. Plus, which function prime is 4x?
2x squared.
Perfect. Awesome. Last question. Which function prime is 2?
2x.
Perfect. All I have to do is only plug in 4, because when I plug in 0 in this polynomial, 0, 0, 0. So I only have 4 to the third plus 2 times 16 plus 4 times 2, which is 8. So this is 64, this is 32, and this is 8. So this is 40 plus 64, 104, and I remember it was 104. Piece of cake, isn't it? Well, I have to caution you on one thing. This is a lucky situation, right? Most of them that we will discuss, they're gonna be like this, but we will not always be able to come up with the antiderivative. No, we will not. And I'll give you an example before I show the last one. For example, e to x cubed dx from whatever you want, you're not going to be able to find f of x. Okay, I don't know, from 0 to 1. You're not going to be able to find f of x. It's not possible by hand. So the antiderivative is eluding us here. We can't find this. But we will be able to approximate it. We will always be able to approximate for the integral from 0 to 1 using, let's say, 4 subintervals, blah, blah, blah. Leftmost point, rightmost point, midpoint, whatever you want to do. We will always be able to find an approximation. So this is not possible. But the approximation always, yes, is.
I was wondering, what happened to the plus c?
Okay, very good. So the integral from f of x dx from a to b is f of x plus a constant c from a to b. I plug in b, f of b plus c minus, I plug in a. Okay, so then f of b plus c minus f of a minus c, f of b minus f of a. Is this okay?
Yeah, that makes sense. Thanks.
Perfect. So the approximation is always possible, but the exact, in certain situations, we will not be able to. Okay, so now let's check the last one that we worked on. So we're on page 10, and we had the integral from 1 to 2, you said, 2x cubed plus 5x plus 1 dx. Okay, perfect. So can anyone give us which function prime is 2x cubed?
X 4 over 4.
Awesome, thank you very much. Plus 5. Which function prime is x?
Is it 5x squared over 2?
Perfect. And which function prime is 1?
It's just x.
Perfect. So I'll simplify by 2, and I have x to the 4th over 2 plus 5/2 x squared plus x. This time I have to plug in both because this is not 0. So I plug in 2. 2 to the 4th, 16 divided by 2, 8, plus 4 over 2, 2, plus 10, plus 2. But careful, minus. Better to put it in parentheses so you don't forget something. 1/2, 5/2, and 1. 1/2, 5/2 plus 1. Good. Now, This is 20 minus 5/2 plus 1/2 is 6/2, which is 3. 3 plus 1 is 4. So this is the way we evaluate definite integrals. Now, what if I ask, let's evaluate the integral from -3 to 4 from 1/x dx? What would you say? Anyone? It's okay if you're wrong.
ln x.
Say it again.
ln x.
Okay.
Right?
FTC not applicable because since f of x, which is 1/x, is not
continuous.
specifically at x equals 0. So FTC is not applicable because we always have to check when we are asked to find the definite integral, definite, on a function, dx. If this function is not continuous on this interval, then the fundamental theorem of calculus is not applicable. So this is the major condition imposed by FTC.